Step outside right now, without a coat, without shoes, and just breathe. That single automatic action, the one you haven't thought about once today, is the exact thing that would kill you in under 2 minutes on the surface of Mars. Not from cold, not from radiation, from your own blood boiling at body temperature, because Mars's atmospheric pressure is so low that liquid inside your body would start vaporizing the moment it was exposed. And yet Mars is still, by a wide margin, the most realistic off-world destination humanity has for actually building a permanent settlement. So the real question isn't really, can humans survive on Mars? It's far stranger than that. What specifically has to be engineered perfectly and kept running forever to keep a fundamentally fragile Earth body alive on a planet that is actively hostile to nearly everything that body needs to function? It helps to understand exactly why Mars, out of every other body in the solar system, keeps winning this argument despite how genuinely hostile it is. The Moon is closer, only about 3 days away compared to Mars's 6 to 9 months, but it has essentially no atmosphere at all, no meaningful water ice outside a few permanently shadowed polar craters, and a 2-week long lunar night that would demand an entirely different, arguably harder power generation problem. Venus has a thick atmosphere and gravity close to Earth's, but its surface temperature averages around 465 degrees Celsius, hot enough to melt lead, with atmospheric pressure roughly 90 times Earth's, crushing enough to destroy most spacecraft within hours of landing. Mars, by comparison, sits in an uncomfortable but genuinely workable middle ground. A real day-night cycle close to Earth's own, confirmed accessible water ice, a thin but real atmosphere that at least offers some resources to work with, and gravity strong enough that long-term human health effects, while still a concern, are expected to be considerably less severe than the zero-gravity astronauts already tolerate for months at a time aboard the International Space Station. Mars isn't survivable because it's easy. It's the target because, among a very short list of genuinely terrible options, it's the least impossible. Let's start with the most immediate problem, the one that would kill you fastest: pressure and breathable air. Mars's atmosphere is roughly 1% the density of Earth's, and it's almost entirely carbon dioxide, over 95% of it, with barely a trace of oxygen. Step outside a habitat without a pressurized suit, and you wouldn't simply suffocate the way you would in, say, a sealed room on Earth. Medical researchers studying rapid decompression, largely from decades of aviation and early spaceflight incident data, describe a specific condition called ebullism, where the dramatic pressure drop causes water in your blood and soft tissues to literally boil at normal body temperature, since boiling point depends directly on surrounding pressure, not just heat. You'd lose useful consciousness within roughly 15 seconds as blood stops effectively carrying oxygen to your brain, and without immediate repressurization, death would follow within 1 to 2 minutes. This is why every single Mars mission architecture, without exception, is built around one uncompromising rule. Humans on the Martian surface exist either inside a pressurized habitat, inside a pressurized rover, or inside a pressurized suit, permanently, with zero unprotected exposure ever considered survivable, even briefly. Temperature is the next problem, and it's stranger than most people expect because Mars isn't uniformly frozen. It's wildly inconsistent. Average surface temperature sits around -63 degrees Celsius, brutally cold by any Earth standard, but NASA's Curiosity and Perseverance rovers have both recorded equatorial daytime temperatures reaching a relatively mild 20 degrees Celsius in Martian summer, before plunging to -70 or lower the very same night. That swing happens because Mars's thin atmosphere holds almost no heat, so unlike Earth, where the atmosphere acts like insulation smoothing out day to night temperature swings, Mars loses heat into space almost as fast as sunlight can warm the ground. Engineers designing habitat exteriors have to account for materials expanding and contracting dramatically within a single Martian day, called a sol, which is only about 40 minutes longer than an Earth day, a detail that itself matters enormously for crew, sleep cycles, and mission scheduling across a multi-year stay. Radiation is where things get genuinely dangerous over the long term, in a way that doesn't announce itself immediately the way pressure loss does. Mars lost its global magnetic field roughly 4 billion years ago, and without one, combined with that extremely thin atmosphere, the surface receives significantly higher doses of both galactic cosmic radiation and solar radiation than Earth's surface, which is shielded by both a strong magnetic field and a thick atmosphere. NASA's Curiosity rover carries an instrument called RIDE, The Radiation Assessment Detector, which has been measuring surface radiation levels continuously since 2012. Its data suggests that an astronaut spending roughly 3 years on a full round trip Mars mission, including transit time, would accumulate a radiation dose considered to meaningfully increase lifetime cancer risk under current career radiation limits set by NASA for astronauts. Long-duration habitat designs address this primarily through mass shielding, thick regolith, the loose rocky Martian soil piled over habitat structures, or, in some newer proposals, water itself used as a radiation-absorbing wall, which means the water colonists desperately need to drink is doing double duty, protecting them from an entirely separate threat trying to kill them slowly instead of instantly. Now, here's what's genuinely fascinating about food and water specifically. Mars isn't actually short on raw material, it's short on accessible, usable material. Water exists as ice, confirmed in large quantities by NASA's Mars Reconnaissance Orbiter beneath the surface at the poles and across several mid-latitude regions, in some places forming glaciers substantial by Earth standards. But at Mars's atmospheric pressure, liquid water can't stably exist exposed on the surface at all. It would flash to vapor almost immediately, so every water system has to be a sealed, pressurized extraction and processing loop from the moment ice is mined to the moment it reaches a crew member's mouth. Oxygen presents a similar story. NASA's MOXIE experiment, flown aboard the Perseverance rover and successfully tested multiple times starting in 2021, proved that oxygen can be extracted directly from Mars's carbon dioxide-rich atmosphere through a chemical process called solid oxide electrolysis, essentially splitting CO2 molecules to isolate breathable oxygen. It's a genuinely major proof of concept, since a full-scale version of that technology could theoretically produce not just breathing air, but oxidizer for rocket fuel needed for the return trip home, meaning astronauts could, in principle, manufacture their own way back to Earth using nothing but the Martian atmosphere itself. Food is where things get less solved and considerably more experimental. Growing crops directly in Martian regolith is genuinely difficult, since Martian soil contains perchlorates, a class of chemical compounds toxic to humans and harmful to most plant life, requiring the soil to be chemically treated or entirely bypassed using hydroponic or aeroponic systems, instead growing plants in nutrient solution or mist rather than soil at all. Researchers at institutions including Wageningen University in the Netherlands have run multi-year experiments growing crops in Mars simulant soil under controlled conditions, successfully cultivating tomatoes, peas, rye, and several other crops, though yields and nutritional completeness under actual Martian light and radiation conditions remain a significant open research question, not a settled one. Most realistic near-term mission architectures assume a hybrid approach, pre-positioned food supplies shipped ahead of any crewed mission, combined with a gradually scaling up hydroponic system intended to reduce, not eliminate, dependence on resupply from Earth, since a single resupply launch can cost tens of millions of dollars and take anywhere from 6 to 9 months to actually arrive. Distance itself creates a problem that has nothing to do with biology and everything to do with communication and independence, depending on where Earth and Mars are in their respective orbits. One-way radio communication delay ranges from about 4 minutes at closest approach to over 24 minutes at their most distant separation. That means real-time conversation with mission control is simply impossible for most of any Mars mission. If something breaks, a life support failure, a medical emergency, a habitat breach, the crew has to diagnose and resolve it themselves in the moment, without the option of immediately asking Earth what to do and getting an answer back in any useful time frame. This single fact reshapes mission design more than almost any other factor, driving heavy investment in redundant systems, extensive crew medical and engineering cross-training, and increasingly onboard AI diagnostic systems designed to flag and help troubleshoot technical failures independently of Earth-based support. The psychological dimension of this might be the most underappreciated survival factor of all, precisely because it doesn't show up on an engineering spec sheet the way pressure or radiation numbers do. Russia's Mars 500 experiment, conducted between 2010 and 2011, sealed 6 volunteers inside a mock spacecraft facility for 520 days. The approximate round trip duration of an actual Mars mission, with no real contact with the outside world beyond communication delays deliberately matched to simulate real Mars mission conditions. Researchers monitoring the crew documented measurable declines in mood, sleep quality, and physical activity levels for several crew members as the isolation wore on, alongside noticeable shifts in group dynamics and occasional conflict, even though every participant was a screened, psychologically robust volunteer selected specifically for the experiment. NASA's SpaceX program, running multiple isolation missions on the slopes of Mauna Loa in Hawaii, specifically chosen for its Mars-like terrain, found similar patterns, including that resource anxiety, worrying about water, oxygen, and food systems, became a significant and measurable psychological stressor over time, even in simulations where an actual physical shortage never occurred even once. The lesson researchers consistently draw from both programs is blunt. Keeping a Mars crew alive isn't only a life support engineering problem, it's simultaneously a sustained, multi-year psychology problem. And mission planners now treat crew psychological support systems as being every bit as mission critical as oxygen generators or water recyclers. Gravity itself turns out to be a slower, quieter threat that doesn't kill anyone directly but changes the entire mission timeline. Mars's surface gravity is about 38% of Earth's, and while research on Martian gravity's specific long-term effects remains limited, since no human has actually lived under partial gravity for an extended period, decades of data from astronauts on the International Space Station in zero gravity show measurable bone density loss and muscle atrophy occurring within months without rigorous, near-daily exercise countermeasures. Mars mission architectures assume similar, though likely less severe, effects will require dedicated onboard exercise equipment and strict daily routines for any crew member spending an extended stay on the surface, adding yet another daily non-negotiable task to a mission schedule already packed with habitat maintenance, scientific research, and life support monitoring. Dust adds a genuinely underestimated layer of difficulty on top of everything else, because Martian dust isn't like sand or dirt on Earth. It's extremely fine, electrostatically charged, and mildly abrasive, and it clings to nearly everything it touches, including spacesuit joints, solar panel surfaces, and airlock seals. NASA's own Spirit and Opportunity rover missions were ultimately ended years apart, largely because accumulated dust on their solar panels eventually blocked enough sunlight to starve them of power. Mars also experiences genuinely massive dust storms, occasionally growing large enough to envelop the entire planet for weeks at a time, as happened in 2018, which is precisely what ended Opportunity's mission after nearly 15 years of continuous operation. Any long-term human habitat has to be engineered specifically around dust mitigation. Airlocks designed to strip dust off suits before crew re-enter living spaces, redundant power generation that doesn't rely purely on solar panels that could be blacked out for weeks, and maintenance schedules built entirely around a substance that Earth-based engineering simply never had to seriously account for before. There's also real, unresolved debate among mission planners and engineers about the best overall approach to actually getting a sustainable human presence established, and it's worth understanding because it shapes which specific technologies get funded and developed first. Aerospace engineer Robert Zubrin, founder of the Mars Society, has long advocated for what's called Mars Direct, an approach built around in situ resource utilization, essentially manufacturing return fuel and other critical resources directly on Mars using local materials, specifically to avoid the enormous cost and complexity of hauling every single resource from Earth. SpaceX's Starship program has adopted a broadly similar philosophy, with Mars mission architecture explicitly built around eventually refueling spacecraft using propellant manufactured on the Martian surface itself. The competing school of thought favors a more incremental approach, smaller robotic and short-duration crewed missions first, deliberately building up infrastructure, tested water and oxygen systems, and radiation, hardened habitats over multiple separate missions before ever committing to a permanent, continuously crewed settlement. Neither camp seriously disputes the underlying survival science we've just walked through: pressure, temperature, radiation, water, food, isolation, gravity. The disagreement is almost entirely about sequencing, about which order to solve these compounding problems in, and how much risk to accept at each individual stage along the way. One increasingly popular idea among habitat designers sidesteps several of these problems at once by going underground, literally. Mars, like the Moon, has confirmed lava tubes, long underground tunnels carved out by ancient volcanic activity, some detected by orbital imaging with openings wide enough to fit an entire habitat structure inside. Researchers studying these formations point out that a lava tube habitat would get several critical protections, essentially for free. Several meters of solid rock overhead provide substantial radiation shielding without needing to haul or pile artificial shielding material, a stable underground temperature, avoiding the brutal daily swings on the surface, and physical protection from micrometeorite impacts and dust storms entirely. The trade-off is engineering difficulty. Sealing a naturally formed underground space against Mars's thin atmosphere and pressurizing it reliably is a genuinely different challenge than building a surface structure from scratch, and it requires finding a suitable lava tube close enough to other mission critical resources, particularly accessible water ice, to actually be practical rather than purely theoretical. The return journey itself, often treated as an afterthought in popular discussion, is arguably as dangerous as anything already covered, precisely because it happens after months or years of the human body adapting to a lower gravity, higher radiation environment. Astronauts returning from extended stays aboard the International Space Station already require weeks of intensive physical rehabilitation to reacclimate to Earth's full gravity, even after missions in zero gravity lasting under a year, with documented issues including significant balance disruption, cardiovascular deconditioning, and continued bone density recovery taking months longer than the mission itself. A Mars crew would face a similar readaptation after spending over a year at partial Martian gravity, layered on top of a multi-month zero gravity transit back to Earth, meaning the physiological stress doesn't end when the spacecraft leaves Martian orbit, it simply changes shape. Flight surgeons involved in long-duration spaceflight research have specifically flagged this compounded return scenario: low gravity followed by zero gravity followed by a sudden return to full Earth gravity, as one of the least studied and potentially most physically demanding phases of any full-round trip Mars mission, precisely because no human crew has ever actually experienced that exact sequence before. There's also the accumulated radiation dose to reckon with once the mission is actually over, not just during it. NASA's current career radiation exposure limits for astronauts are calculated specifically to keep lifetime cancer risk increases below a defined threshold, but a single full Mars mission, transit plus surface stay plus return transit, could consume a substantial fraction. In some mission profile estimates the majority of an astronaut's entire career radiation allowance in one single trip. That reality already shapes crew selection and mission planning today, limiting how many long-duration deep space missions any individual astronaut could realistically be assigned across an entire career. And it's part of why radiation shielding research, whether through regolith, water walls, or underground lava tube habitats, isn't a minor engineering detail. It's a direct constraint on how many people can safely make the trip at all, and how many times any single person could ever safely go. So here's the honest, layered reality underneath all of this. Getting humans to Mars is, at this point, largely a solved rocketry problem, difficult and expensive, but conceptually understood, and companies like SpaceX have explicitly built mission architectures like Starship specifically around eventually solving exactly that piece, keeping humans alive once there is a different category of problem entirely, a permanent, compounding engineering and psychological challenge involving airtight pressure systems, radiation shielding, closed-loop water and oxygen recycling, experimental agriculture, extreme temperature swings, communication delays measured in minutes rather than milliseconds, and the sustained mental toll of genuine, prolonged isolation from everything and everyone on Earth. Every single one of those systems has to work correctly, simultaneously, for years at a stretch, because on Mars, there's no atmosphere to fall back on if even one of them quietly fails. The next time you take an unconscious breath of ordinary Earth air, remember that recreating that single, effortless action, safely, reliably, for years at a time, on another planet entirely, might genuinely be the single hardest engineering problem human civilization has ever seriously attempted to solve. And maybe that's genuinely the most honest way to frame the entire question of Mars once you strip away the launch footage and the mission patch optimism. We didn't evolve for this. Every system a Mars settlement needs, sealed pressure, filtered radiation, recycled water, manufactured oxygen, engineered food, is a direct, deliberate substitute for something Earth simply hands every living human for free, silently, every single second, without asking for anything in return. Mars doesn't offer that deal. It demands that humans build, entirely from scratch, the exact planetary life support system Earth spent 4.5 billion years assembling on its own, and then keep every piece of that substitute running flawlessly, forever, with no atmosphere, no magnetic field, and no margin for a bad week. Whether or not that's ultimately worth attempting is a genuinely open question. But it's worth remembering the next time someone talks about Mars as humanity's next home. That home was never really the hard part. Staying alive long enough to make it one is.